All right. Good morning, everyone. Let's start. So we are learning the different kinds of adders. So the first straightforward adder is this ripple carry adder. And we know that it has the problem of the long carry propagation. And then this is some so we can write the output of one before adder in terms of intermediate values. We'll use these results frequently. Now you better to remember these properties. First, they generate and propagate functions of A and B only. Second, we can express the output, carry output, and the sum output of a full bit adder in terms of this GP and carry in. Carry out is generate plus the product of propagate and carry in. The sum output is the propagate exclusive or carry in. And then we learned this first type of fast adder called carry bypass adder, also known as carry skip adder. So basically, we divide a long adder into stages. Each stage contains certain bits. And if a propagate, if a carry in has the worst case of propagating through a stage, then this can be detected early. And we can use a multiplexer to bypass it from the nominal adder cells. So we can bypass it directly to next stage. With this, we can improve the speed. And we have discussed this formula earlier. And this is a comparison. Next, we're going to learn a second type of fast adder called carry select adder. Now, again, here, so to generate the carry out for each adder cell, we need the carry in information generated CO equal to generated plus propagate times carry in. So to generate the carry out, we need this information. We need to wait for CI, and that's all. That's the root of the problem in the long delay. So an approach without waiting the delay is to assume that CI is known, carry in is known. There are only two possibilities. CI is either 0 or 1. Only two possibilities, right? So we can calculate CO for both possibilities in advance without waiting for CI. So here the idea is to
generate the CO for both cases. For when the carry in is 0 or 1. For both possibilities, we calculate the output. And we will do the selection of the actual carry out, where carry in comes in when the carry input is available. Here is a is a stage in carry select adder. This stage contains, for example, 4 bits. First, we need to have a setup stage. Need to generate a P and a G for each bit in this stage. Propagate and generate. They are functions of A and B only. So they do not need to wait for CI. So this is a setup. Then the carry out for each bit in this stage needs to, usually needs to have the information of carry in, but we calculate the carry out for all the bits here. For both cases for carry in. So assume carry in is 0, we can calculate a set of carry outputs without waiting. Another set of carry outputs, assuming the carry in is 1. So we have two hardwares, two set of hardwares. Two set of hardware to calculate the carry out without waiting. So you see the symbol here, the diagram here is not this. So this carrier output is generated based on setup, and the assumption of the carry in is 0. This is another set of hardware. It calculated the carry out using the setup and the P and G signal, P and G signal here, and assuming carry in is 1. So these two are in parallel. Two sets of hardware performs the calculations simultaneously with different assumptions. So we get 2 sets of carry out values under 2 assumptions. And when the carry in of this stage is available, we select one set of this stage, one set, select one of these 2 sets, and perform the sum calculation finally. And the sum calculation, the sum is P exclusive for CI. It needs CI's value. And CI here is for each bit. It's basically CO's, the previous bit's CO's value. So when the carrier is available, the sum can generate immediately. So that's the main idea. We perform the calculation for all the for both possibility of the carry in without waiting. Then when carry in arrives, we just select one set of the data. So do you have any questions regarding this idea? So this is the key idea. Next, I'll give you some illustrations. Okay. Now, this is an example. Say we have we wanted to build a 16-bit adders, 16-bit adder. Using this carry select method. So we divide into a number of groups, say 4 groups. So each group contains 4 bits. First stage is bit 0 to 3. Second stage, bit 4 to 7. Third stage, bit 8 to 11. And finally, bit 12 to 15. The inputs are here. Okay. So say for second group here, normally it needs to wait for the carry out of previous stage before it can generate its results. But here, we have 2 sets of hardwares, assuming the output of previous stage, carry out of previous stage is 0. We have hardware here. Output of previous stage is 1. We carry hardware here. Then a multiplexer here, waiting for the result from previous stage. Okay, and then this 4 stages. The first 3 rows of these 4 stages, they do the calculations simultaneously without waiting for each other, because they have this assumption. And then they carry out the calculations for both the input possibilities. So they can do the calculation at the same time without waiting for the previous stages. So the critical path is here. The first stage needs to set up, and these 2 rows perform calculations at the same time. And then there's a delay generate in this multiplexer. And this propagates to here, and to select the left or right result here. But this result is already available, waiting for the multiplexer to perform the selection. So this part of the circuit is not the critical path. It won't affect the worst case delay. So the critical path is here. And then the carrier arrives at the input of third stage. When it arrives, the 2 sets of possibilities are already available. Okay, then there is another delay by the multiplexer. Then finally to the final stage is multiplexer. And then the sum generation, here it needs CI's value. So to generate this sum, it needs to wait for this position signal to be ready. Okay, then perform the final summation for the final stages. So this is the critical path. Yes.
Then for the last equation for the carrier and multiplexer, there are no synchronous because there are n bit of carrier.
Yeah, I haven't talked about this. Let me talk.
Why would we need to use the sum generator? Because the result is already calculated in 0 period.
This, yeah, let me explain this one by one. So for the sum calculation, so this 2 pi is not to generate the sum, it's to generate the CO. for all the bits there. The sum still needs to perform here. So this carry stage is to, for some is to generate a C12, C13, C14, C15 to generate this. And from this, you exclusive with exclusive or with P12. No, I think this exclusive was P13. This exclusive was P14. Exclusive was 15, and the previous one exclusive all was P12. Then you get the sum of those are to generate carry out. Only the carry. But the sum needs the carry. To get the sum, you need the carry. Okay, so lastly, this part. Now I haven't explained this equation. Let me explain this. So the critical path has this delay. First is setup time. And then the time produced, the time needed, the delay time needed in this carry generation. There is only one of them, 0 carry or 1 carry, because they are in parallel. And the number of bits in each stage is n over m. In this notation, we have m stages, a total of n bits. So the number of bits in each stage is n of m. Okay. So each stage is n over m. That's the notation used here. Okay, so so in this carry generation, it has n over m bits. So each data cell has this carry delay, a T carry. So that's the delay involved here. And then we have here m multiplexers. The critical path contain 4 multiplexers. Yeah, m multiplexers. That's the delay. And finally, the sum for the final stage. Of course, it will also take a time for this sum generation, but they will occur earlier than the last stage. The signal here is earlier than the signal here. Okay, so that's the error delay. Now let me ask you this question. Say, if you wanted to optimize the delay, how would you choose the number of stages? N, yeah. Just tell me the method. I want to optimize the delay, minimize the delay. N is given. The M is subject to your choice. What would you do? Yes.
Approximately square root of n.
Yes, usually that's the case. But the method is this: you take the partial derivative of t adder with respect to n, and you set this partial derivative to 0 and solve for n. And the result you get is m is the square root of n. But if this is not integer, then you need to adjust it to make it an integer. Good answer. So I would like to mention that this slide has been updated. There are 2 slides posted in the Blackboard. In the updated slide, you have this notation. And this even division of stages, even division. I mean, each stage have the same block size. Such kind of carry select adder is called a linear carry select adder. It's linear because the adder is a linear function of n, and since we have an a linear term before carry select adder, it implies that there must be another kind of carry select adder, and we will show that. But before showing the other carry select adder, let me show you one property. One thing that this linear carry select adder has not fully optimized the delay. Let's consider this 16-bit adder. Each stage has 4 bits. Now let's assume the assume this T carry, T multiplex, T sum, T setup, they are all equal. These logic blocks produce the same delay to simplify the analysis. The T setup, T carry, T multiplex, T sum, they are all 1 unit of delay. Now let's check the delay at different positions. So let's say time 0 is the time when the input data, 2 input words arrives. Then after the setup time, the output has a 1 unit of delay. Here. This setup output is also go to this 1 carrier block directly without going through the 0 carry delay. These are 2 parallel blocks. So delay here is 1. And for each carry block, it has 4 bits. So it will generate a delay of 4 units. So at the output of each carry block here, the delay is 5. The time that it is available is at time 5. Are you okay with this? Okay, good. Now, on this critical path, after the multiplexer, it has another propagation delay, so the output is available at time 6. And all these above 3 rows, they produce the output at the same time. They run simultaneously. So the output of the second stage, output of the carry block of the second stage is available at time 5. For the third block is also time 5. For the fourth block is also time 5. And now along this critical path, the delay is 6 here, 7 here, 8 here. Now finally, after this delay is not delay 9, so 9 and 10. So that's critical path. The longest delay is 10. But now when you look at the last multiplexer's input, its carrier in is available at time 8. But this result carry out for last stage, waiting for selection, are available at time 5 earlier than the selection multiplexer selection input by 3 units, by 3 time units. And this is not the optimal selection. And this is intrinsic if we have this even block size, the same block size. You must have this property. At the last stage, the selection signal, a multiplexer selection signal arrives later than these 2 inputs of multiplexer. So some people think of improving this. So before I move to the next stage, can you think of some solution to make the multiplexer's upside and left side input to arrive at the same time? So you can vary the size of each block. So the answer is to make a first stage to have fewer number of bits, and it progressively increase the number of bits along the stages. As shown here, say I assign 2 bits to first stage, 3 bits to the second stage, 4 bits to the third stage, and 5 bits to the fourth stage. If we only have 4 stages, then the total number of bits is 14. But if we do this progressively wider width for the stages, then we get this optimized delay. Let's check the output, the carry output available arrival time of these 4 stages. Setup is 1 unit delay, and first stage we have 2 units delay, so the output is 1 plus 2. Here is 3 units. And the second stage, because the carry is 3 bit wide, so the output here is 1 plus 3 is 4. For the third stage, setup is output is available at time 1, and the carry block has a length of 4 bits. So 1 plus 4 is 5. And fourth stage is 1 plus 5, 5 bits long, 5 bits wide. So it's here, the top side of multiplexer is available at time 6. Now let's consider the multiplexer's path. So this is 3 time 3. The signal available at the time 3. Our multiplexer is available at time 4, and this 4 is matched to 4 here. And the left and top side inputs of multiplexer are available at the same time. And this further propagates to the next multiplexers. The time 5 on the left of this multiplexer, time 5 on the top. So equal arrival time. So that's very good. Same to the last multiplexer stage. Okay, so that's the idea. Make the word length progressively wider. Say if we have a 14-bit adder, then you can calculate that the available time is 6 plus 1 is 7. Delay is 7, and you can derive it. You can derive equation to calculate the total delay along critical path, and you can find that the delay is a square root function of n. So we can people name this carry slide adder as square root carry slide adder. So any questions regarding this carry slide adder? Well, the basic idea is simple. So we divide the whole adder into a number of stages. And for each stage, we don't wait for the carry in and perform, we calculate the carry out, assuming the both possibilities of the is carry in. So no need to wait for the carry in. That's the key idea. This plot shows and this plot is a comparison of the delay for this ripple adder, linear carry slide adder, square root carry slide adder. So for long big words, the carry slide adder offers much better performance than ripple carry adder. And the square root carry slide adder offer further advantage in terms of speed over linear carry slide adder for long big words. Okay. I think let me take a 3 minutes break here. All right, let's continue. So now, by now we have learned the two type of fast adders, the carrier skip and the carry select adders. And next we are studying a third type of fast adder. Again, this is important table. I use these properties. So this intermediate value generate and propagate of carrier. And the carry out, so this is a full bit, 1 bit full adder. The carry out and sum can be expressed as functions of G, P, and CI. Next type of fast adder is called carry look ahead adder. So the aim is also to get around the rippling effect of the carry. So-called to look ahead of the carry. Now, the carry logic can be written recursively as below. I say the carry out of first bit is the generate plus the product of propagate and carry in. So that's just this equation. Just this equation. Let's call this carry out as C1. Then C2 is G1 plus P1 times C1. And we can replace the C1's value using its previous expression recursively. So we obtain this function. So here the property is that C2 is a function of this G P values and the C0 value. These are all the G and all the P's value can be obtained immediately when the input comes in, not immediately after a short delay. You don't need to wait for the carry in. And the C0 is the primary carry in. It's available immediately. So for this, if we express C2 in this way, there's no need to wait for the carry to propagate stage by stage. Further express for the carry out of next stage, by the same approach, write it exclusively. We can write a C3 in terms of G2, P2, G1, G0, as well as C0. And C4 in this way, in G3, P3, G2, G1, G0, also propagate and generate signals. And the term contains the carrier in of first stage, C0. Logically, we can build it in this way. Say this is first adder, first full adder, first bit. So this is just a normal one. And then the second bit adder, this C1 is its input C1 is not connected to the C out of first adder. It's generated directly from a combinational logic block. This combination logic block has functions of is a function of C0 and propagate P0 and G0. They are available very quickly. And same for the third bit. It's not its carry in is not connected to the carry out of previous stage, but it's directly generated from such a combination logic. And for a third bit, it's like this. And for the output of fourth bit, the carry output of fourth bit, if required, it is generated by such a circuit. And conceptually, we can express such an adder in this way. So we have some block here. The sum is generated using this equation is P exclusive of Ci. And P says P so for S0 is P0 exclusive with Ci of this stage. Ci is wide available, and then this for second stage, its carrier input is generated using this P and G signal. Okay, so we have some combinational logic here. It's becomes the height of this block becomes higher progressively. This is because to generate the carry for a later stage, the combinational logic has a greater number of inputs. I say the fourth stage, it has a term that contains 5 inputs. And 5 input for logic block that contains 5 input, its delay will be longer than the same block with fewer inputs. And this higher is a way to represent the delay. Okay, the idea here is that the carrier signal can be generated from all the P and G signals without waiting for intermediate carrier signals. And this is named a carrier look ahead. This expression looks like to look ahead for the carrier. So, do you have questions with this concept? Now, there is a problem with this. The problem is that the delay could be long if you you do this repetitively for all the bits. Say if you have 16 bit, and final stage may contain an gate of 17 inputs. That delay could be very long. So the speed of carrier adder is only fast for relatively small number of bits, say 4 bits, or maybe 5 or 6 bits. And it can be faster than the usual ripple carry adder. For longer bits, if you directly apply this technique, it won't be offering any speed advantage. But there is a way there is a hierarchical way to use this concept to improve the speed for long adder. So those gates in the carrier look ahead adder grows in complexity at each bit position, but we can build a carrier look ahead tree as a hierarchy of gates. Let me illustrate the concept here. So this is the first bit, first bit adder as generated plus the product of propagate and carry in. This Ci0 means the carry in of 0 bit. CO0 means carry out of 0 bit. Just this equation. This equation there. CO1 applying this equation is G1 plus propagate 1 times CI1. And then if we apply CI1, which is CO0, output of P0, and we group the terms in this way. Then the first term can be regarded as the generate signal of the group that contains bit 0 and bit 1. This is the generator of this 2-bit group, bit 0 and bit 1 combined as a one group. This is the generate signal of this group. And this is the propagate. P1 times P0 is propagate, the net propagation of this group. CI is 0. So it may propagate to the output of this group when this P1, P0. This group, when this group propagates, is true. As group generate in the group propagate concept. Just like a tree, we have a group, the big 1 into 0. It has carried in C0, CI 0 is a group, and it has input A and B. Then it can generate 2 intermediate output, propagate. And generate and propagate, let's call this group propagate 1 to 0. It's a group generate 1 to 0. This group may pass. If this propagate is true, then this propagate will at least carry in the propagate to the next stage through the whole group. If this generator is true, then the carry output will be true. Carry output will be true. It's treat this combined bits as a block, as a bit, like that. If we further go along this direction, say the third bit, it carry out CO2 is third bit. It can be expressed in this way. We had this expression earlier. Then we can regroup it in this format. I should put this as C01. This should be C01. Let me make this correction. So you can express as this. So if we treat bit 1 and bit 2 as a group, so this group's generate is this. Group generate function equals to G2 plus P2 times G1. It's group generate. The group generate is a function of individual bits generate and propagate signals. And this is group propagate. It's a product of individual bits propagate signal. And then this is the group's input carrier. So we can continue building the tree hierarchically. And this group propagate idea has been encountered before. Do you recall anything similar to this concept? the carrier skip adder. We have this multiplexer layer to skip a carry in, to directly pass the carry in to the output of that stage. That the multiplexer has a selection input equals to the product of all the propagate signal of the stages. So that's something similar. Huh? But anyway, here is the group generate and group propagate. So we can combine this groups up to our wish. Say, this has been shown before. Say we combine group bit 1 to 0 as a group, then we have a group propagate equals to product of this P1, P0, and group generate equal to this. That's shown. That's the first equation here. This is the group propagate, group generate at first time. This is group propagate. See, group generate is this, and group propagate is that product. Is easy to remember. So we can form groups like that. Now let's consider a AB adder. We wanted to see how the last stage, last bits carry output is generate. We can do it in this in this way in order to reduce the delay. Okay. Now first we generate the P and G signal for all the bits. This is easy without needing to wait for the carry in. P and G for all bits are generated very quickly. And then for bit 1 and 0, we combine them into a group. So the group propagate and the group generated signal depends on this these P and G inputs as shown in this equation here. These two. So this is a group propagate. Little group output P and G. P and G output of the group depends on P and G of individual input pin. P and G signal of the input. So and then we can combine bit 3 and bit 2 into a group. The group propagate, group generate signal will be generated using a function similar to this. And then we combine P1, and this is a group propagate for 1, 0, group propagate for 3, 0. So these two parts are combined into another group which contains 4 bits. Just do this hierarchically. I just treat this as one input. This is another input. I do this hierarchically. Okay, then this before B5 combined and 6, 7 combined. Then this 2 combined into group 7 to 4, and then this 2, 4 big groups are combined to an AB group. Now, so let's say if the generate signal is high, this group generate, this G7 to 0 is this group generate is high, then the carrier out for the last bit is high. Or if this propagate, group propagate is high, then it's C0, the first carry in will propagate to the output. So the worst case delay is this. When we need to propagate from bit 0, propagate a carrier from bit 0 to last bit, it will go through this stage, this stage, and this stage. But go through 3 stages. And here we have this tree structure of this primary stages. So in the last stage we have 1 element. Second last we have 2 elements, and 4 elements in the third last stage. So this is such an exponential relationship. So number of stage is an so the total number of gates is an exponential function of stages. So if we say if total number of stages, let me give you a name. Say total number of stages says is n. Then total number of gates is n. Number of stages here is n. Call it n. This -1 is something minor. So here we have 3 stages. Three stages. So it contains 8. Actually 7 elements. 8 elements. So you can find that delay is actually say number of stage n is ignore this one. It is a log function of n to the base 2, log of base 2. And this can significantly reduce the number of stages. Say if you have 16 bits, then log 16 to base 2 is what? Is 5, right? You have only 5 stages. The signal only need to pass 5 stages in the worst case. And compared to the ripple adder, you need to pass through 63 stages. But this will not suppress a large number into a small number. So it can reduce the delay significantly. Any questions regarding this basic idea? Here is not a complete diagram, not a complete picture of the adder. We only show how to generate 3 cases, carry out 3 cases. This is his second last case. And also we know the output of this position and this position. But we don't know the position here, because carry out here, carry out here, carry out here, carry out here. It's other 3 positions. We don't know them yet, right? We only know how to generate carry out for this 3 positions. And we need to generate the carriers at all the individual bit positions. To generate the sum of we need to carry a signal for all the stages. The way to generate it is like this. Here shows a very nice diagram. How we get those carry outputs. let me repeat what we have for bits for carry out of the last bit C7. So C0 is given. Now it will, so we have this combined two bit into one group. 2 and 3 to one group. Then these two bit groups are combined into a 4 bit groups. And further, this 4 bit groups with another 4 bit group combined into one big group. So the C0 for the C7 will pass like this. C0 pass this PG block, a logic block. Then this logic block. Then this logic block to here. C7 is available in that way. And C1 is in this way. So C0 is passes through this to here without is available. Now how about C2? This bit. Because C1 is known and P2, G2 is known. So you can use this equation. Say CO I equal to GI plus PI CII. This for this bit, this is the input, this is output. So for bit 2, you know the P2, G2, and you know C1, right? What you know is the propagate generate of this bit and the carry in. Carry in is C1. So these 3 signals are all known. So you can use a logic block to generate C2. Now for bit 3, as I said, we can have this P0 to we have this now we have this T3 to 0 is a book generate. Propagate, book propagate. Here is called just C3. C3 carry out for C3 group generate plus the product propagate, group propagate and group carry in. You treat this as a group. This as a group. Carry in here. Yeah. So this block will generate a group propagate. Generate. So this can be generated. Therefore, P4 is easy. P4 is known, and C3 is available here. Can we get it here? And for C5, C5 now we have this group containing P5 and P4. Okay. If I use for C5, say C5, I wanted to generate C5. C5. I have a list book.
bit 5 and 4, 5 and 4 is a group. So the group carrying is yeah, group carrying should be the bit before B3.
So this is a group. This block generates a good propagate, good generate signal. It also needs the good input. Good input is now C3. And C6 is simple because C5 is available already. And then there's individual propagate generate combined with its input gives C4. So can you trace this diagram, tree diagram? Do you understand it?
So the important thing is that all these forms a 10 multiplier. P and G is same logic function as shown before.
This is it propagate is like this. A good propagate and a good generate is like this. If you look at the individual, so this individual, but anyway, so here we have this standard format. So this group generate. This group generate. They have the same format. It's present bit generate plus propagate. The product of present propagate plus previous generators input. Same format. It's just an OR gate plus an AND gate. Then this group propagator is a AND gate. So do you see any? Do you have any questions regarding this? So we build this this tree hierarchically. So this is a tree. In another format, the same tree is shown here.
It has a name called Frank tree. Because named by these two persons. So we have this. So this is if we look at A bits here, A bits. This dot is like a P and G generation signal before. Say, if we need to generate, say, consider the S7 last bit here.
So the first two is combined to a good this bit this bit 2 bit 3 another group. Basically it's just to turn this vertical, and you can observe that in worst case signal propagates in this way to B7. And for the for this C1, C2, you have this block like this. It's just turned out to vertical and extend it to 16 bits. And this is one kind of tree. And there are other kind of trees. Many ways to construct these trees. Or carry, look ahead. Most of these vary 3 basic parameters. Radix. What is the branches? So here, if we combine 2 into 1, radix is 2. Sometimes we can combine 4 into 1, then that is radix 4. So we have shown radix 2. Some people go to radix 4. Tree depth is stages, sparseness. Here shows a tree called a congee stone tree. The idea of this is like this. Say we all for B7 we know this path from here to here. So this B0 and 1 combined, B3, B2 and B3 combined. Let's see. Well, you see, this 2 combined pass to this one, and then it accepts this in, and form a 3 big groups, and all the way up. Well, anyway, there are some many combinations, but these are just examples to show you. But what I expect you to know is to understand this one. Basically, it's this one. This one. This is a straightforward. It's a 2 to 1, 2 to 1, 2 to 1 combinations. You can combine. There are many different combinations. You can combine 3 bits into 1. Many ways. Just show you some topologies here. This is one topology. And this is radix 4, congee stone tree. So so say here 4 stages, 4 input, 4 bits are combined into a group in 1 stage. So this is called radix 4. And with higher number of radix, then the number of stages is fewer. So with see, for this 16-bit, it only has 2 layers, 2 layers of this P and G blocks. So it can produce shorter delays. But this is quite dense. You need a lot. You need a lot of P and G blocks. And this is sparse. You have fewer logic blocks, much less dense. But here, this is radix 2, so it requires 4 layers. Okay. So this is a look ahead. Carry look ahead. Our idea here is to combine some bits into a group. And in this group, you can generate for this entire group. Carry can be generated from the entire group or can be propagated through this entire group. Something the condition is similar to the carrier skip adder. Okay, let's it's a long time. Let's take another short break, 2 minutes.
I think why is not this C4? I think it's C3.
If we follow this,
Say, this one, right? This one, 5-4 here, right?
so these two bits are combined into a group, right?
Yeah.
So it's carrying is this one, right?
Yeah.
Carrying is this one.
I mean, but for the equation, I think it should be C4.
Yeah, but here, let's follow this, follow the definition here. This two is a group, so it's some, if you follow this table's notation, this is C0. If you want, this is, if you want, you see.
That's G4 is G4, G5 for G5, five times G4. Is this one?
For the numbering, yeah, if we use this notation, let me see.
Yeah, I think G21 is this G2 plus GP.
CCO2, then this is well, anyway, for the notation, maybe you are right. Let me double check it. But the thing is that you have 2 bits, and this is the input thing. So this is 4 and 5. And you have to carry in.
Yeah.
To this good. Anyway, this is input. Input of this stage or output of previous stage. The carry out of previous stage. As long as you are clear about this. But in notation, pay attention to it. And maybe. But anyway, from the block, if you trace the block.
I think that block is very confusing.
No, it's not confusing. You see.
Because
It's easy, right?
it's not matching is the equation. It is.
Okay, maybe. P1, G1. You know, this is CCO, this is output of first I'll go first, right? I need to propagate to next stage. Anyway, this line said P, this two, right? It's in, it's carried in is from the previous stage here.
Yeah,
It's just trace this.
no, I mean, C0 to C3 is the same with the first equation, but the C5 is not, I think it is not mentioned. I don't know,
Why? But C3 is the input to this group, right? C3 is the input to this group. Input to this group.
Yeah,
Then
and I just want to derive an equation for this graph, and I example.
yeah, let's talk about this later. After class.
Okay.
It's just a matter of the index. Okay. So now we have learned the three types of fast adders. There are other fast adders using different number representations. Here I introduce two of them. One is a method that uses residual number system. Another uses a redundant number system. Let me show you this first one using residual number system. It has a limited carrier propagation. That's a property. Still, all the methods here concentrated on getting around the carrier propagation issue. Now, the method here, the adder here, it uses residual number system. This Chinese remainder theorem. So you can represent a number using residuals. Say, here is an example of this residual number system. I want to represent 700, this number 700, decimal number 700, using a residual number system. Now in this residual number system, I choose this bases, both base 8, 7, 5, and 3. Which means I use 4 digits or 4 bits, so 4 digits to represent this number. The number corresponds to basis 8 is to divide the number you want to represent by 8 and use the remainder for this digit. So 700 divided by 8, remainder is 4. So 4. 700 divided by 7, remainder is 0. So the second basis. 700 divided by 5, remainder is 0. 700 divided by 3 is 1. So a RNS system depends on the basis. Here we use 4. So for 700, the decimal number 700 is represented in this residual number system as this way: 4001. Then why bother this? The most important thing is that when you're doing addition using residual number system, you don't need to care about the carry propagation. No carry propagation. Now let's consider addition of 721. First, we represent each number in this residual number system. So 700 is given is 4001. And 21, you can find it is 5010. Okay, then that now consider addition. The 700 plus 1 so because when you add two numbers and you divide the sum by a number, say A753, the remainder should be the sum of individual remainders. If over 4 does not occur, say let's check the first basis. Is say basis A. Basis is 8. The first number remainder is 4. Second number remainder is 5. Imagine that you put this 4 and 5 outside that block, and so you have a net remainder of 9. But now we are dividing 8. This 9, you can further divide it by 8 and get the final remainder, which is 1, right? So 4 plus 9, 4, and mod 8, remainder is 1. This is straightforward. You just divide the sum by the same number, right? You just put these two numbers, add them together in a decimal way, then perform another module again. From this position, from this digit, you know that for a digit corresponding to module 8, it has nothing to do with other digits. Other digits divided by 7, 5, or 3 won't have an effect on this digit. So there's nothing of carry propagation. Right, these positions are random. You can put A7, 5, 3 in this way, or you can swap it. As long as you are clear that this position is corresponds to a module of say 3 or 5. So there's nothing of carry propagation. That's the key concept that people wanted to explore in order to improve the speed of an adder. Now, if you check the other 3 digits or positions, say for basis 3, the sum of the remainder is 1. Then when you further modulate, to further modulate by 3, so it's still 1. So 1 plus 0 is still 1. And then 0 for the basis 5, this position, 0 plus 1. So remainder will still be 1. And for this position, 7, basis 7, 0 plus 0 is 0, and sum is 0. So final result is 1, 0, 1, 1. You can check that this is equals to 7 to 1. Okay, so no carry propagation. You just take a module. It never have, so for each position, it never has a number greater than the basis. Of course, for each position, you need a certain number of bits to represent it. Here, you need 3 bits to represent each position. Say you need for this 5, you need 3 binary bits to represent a 5. Of course, to calculate 5 plus 4, there will be you need to use binary adder, and there is some carry propagation involved, but that's only limited to 3 bits. So this is called as limit carrier propagation. So this is about sum. And for other, say, multiplication, signed, unsigned, additions, you can refer to this article, and it won't be covered in this course. Just show you a reference to a more informative article. Another number system that can be used to avoid the carry propagation. Before that, here is a summary of the remainder number system. As limited carry propagation, high parallelism in computation. All those individual positions can be calculated in parallel. And you can achieve localized modules. This is beneficial in layout and routing. But that involves some overhead. First, you need to convert the binary number into RNS. And after you get the result, you need to reverse it back into RNS. That's the overhead disadvantage, drawbacks. The remainder number system has found applications in various scenarios, including digital signal processing, such as final impulse response filters, communication and networking, and in packet processing, routing, cloud storage system, fault-tolerant computing, cryptography. I think that let me see if I have time to finish this. I'll just stop it here. Let me stop it here for today. Are there any questions regarding this fast adders? If no, that's all for today. Thank you for coming. If you have questions, you may come. Yeah. Let me stop this.
I think you.
Wait, let me stop this.